Yeah.
I would kind of just like the classic.
Yeah. And one and it's with cheese, bacon, and sour cream.
That would be good. Like sour cream, sure, I can see working well, or like bacon rolls and like pulled pork or something. Like a little.
I gave this lecture. Z-scan?
Yeah,
you talked about that.
I thought so. Yeah, just
There are things in life that are worse.
Yeah, but on Friday I found out about another assignment for today. This is what it's supposed to be. Yeah, the professor posted an assignment on Wednesday, but at least a week. No, he posted it on Wednesday as well. But I asked for an example.
So we only have one side seat.
I was really mad at him. Yes, I'm telling him that he will upload the new assignment. Told the professor and didn't do it, and then he's not
From the experiment of that both sides. So my
Oh, I
question
see. It
is,
was small
possible or
yeah, they're also working.
maybe even
Because he said that the assignment was 50%. But this is only the second assignment.
did we decide when to hold the final exam?
Yes.
Well, I forgot to write on my notes. Could somebody please remind me?
December 13th.
December 13th at.
I think at 1 o'clock.
Oh, okay. It is on my notes.
Yeah. And you've already arranged for a room.
Right. Yes.
Like it's here.
That's right. I remember now. The thing so now I have to ask the people in Rochester when their final exam is. I said final exam 1 p.m., but I forgot which city. Okay. So you can start taping now. So, hello. Any quick questions before we start the lecture? Don't worry. I will work very hard to confuse you, thereby ensuring that there will be plenty of questions during the lecture. So today, I guess there are a number of topics that I rushed through some of the material earlier in the semester to make sure that we got through what had to be gotten through. And now I want to back up and fill in a few of the gaps. There are some very interesting topics that are worth discussing. And so that's today. So today is like from a culinary perspective, this is leftovers. In fact, we just had our Thanksgiving in the U.S., so eating leftovers is really things that are on everyone's mind right now. So that's right, and I'm supposed to avoid that part. So let's talk about something that I will call two-beam coupling. And here's what I mean. Well, different people mean different things by it, but let me consider the following situation. I have a non-linear medium, and at least for now, I don't want to specify what I mean by nonlinear. And I bring in two beams of light. One at frequency omega 1 and another at frequency omega 2. And I will define this to be the z direction. And I ask the question, when is there energy transfer between the two beams? And let's let the angle between the two beams be called theta. And let's assume that theta is large. And again, I'm not going to specify what I mean by large, but we're not talking about the pure forward direction. I mean, here are two beams of light. They intersect in a nonlinear material. Is there energy transfer or is there not? And seems both a useful and a intellectually intriguing question. So how do I want to start off? So at first, I'm going to get my notation right. Okay, so as a first step, let's just assume it's the sort of standard situation. It's an N2 type of nonlinearity, and let's ask, is there energy transfer between the two beams? So let's define our field amplitudes, and it will be instructive to work in the time domain. So the field amplitude is the superposition of A1 e to the I K1 dot R minus omega 1 T plus A2 e to the I K2 dot R minus omega 2T plus complex conjugate. And of course, A1 can be a function of position, because that's what the problem is. We want to know if energy flows between one beam and the other, but to keep the notation simple, I'll just call it A1 and A2. Now let's ask, what does the interference pattern look like? So the interference pattern will be given by some constant that I'll simply call K, because I see that I'm using Gaussian units in this lecture. So it's some constant K times E time domain squared time average. I guess we have to ask what we mean by a time average in this context. If we average over a very long amount of time, even the beat note between the two will disappear. So I don't want to average out everything. I want to average over an optical period, but I don't want to average over the beat note period. Is the way to put this. So then the intensity pattern can be written as K times A1 squared plus A2 squared plus A1 A2 star e to the I Q, which I'll define in a moment, dot R minus delta times T plus complex conjugate. Let me be more careful. This is a curly bracket, and this is a square bracket, and also a curly bracket. And now Q I'll define to be K1 minus K2, and delta I will define to be omega 1 minus omega 2. So this is it's a moving interference pattern. You can't call it a moving stationary pattern because it's moving. So it will be an interference pattern that is moving through the material. Let's take a look at what it would actually look like. So if K2 is in this direction and K1 is in this direction, then we've defined Q to be the difference of the two K vectors. So it's something like this. And now if we plot what this will look like, so here's our material. So the lines of constant phase will be, or intensity in this case, will be perpendicular to Q. So we get an interference pattern that looks like this. And the pattern will move in this direction for for delta greater than 0, and will move in this direction for delta less than 0. Okay, so you have a moving intensity pattern in the material. Now, if delta n is just n2 times I, then this will also be a grating. Well, it's a refractive index. Pattern. Or we can call this a moving grating. And now let's just think this through. If you have a refractive index variation that looks like this, you come in with a beam of light going in this direction, it will reflect off of this grating and end up going in this direction. So let me draw it again like this. If you have this coming in, it will reflect into this direction here. So K1 and K2. So if K1 comes in, this grating by construction is oriented so that K1 will reflect into the K2 direction, and it will be shifted with a Doppler shift. If the grating is moving toward it, then it will pick up energy. If the grating is moving away from it, it will lose energy. So this will be at frequency, well, K2 will be at frequency omega 2. And similarly, if you have the same distribution, and you come in with light like so, it will be reflected into this direction here. So if you come in with K2, it will be reflected into the K1 direction, and always with frequency omega 1, because the grating is either moving toward it or away from it. So it will shift the frequency here. Maybe just write it this way. So isn't this something that nature is so clever, that nature automatically phase matches this in this particular direction? Yes?
What exactly is causing the grade?
Oh, No, I said if n2 is n2i.
I'm not sure what the actual interference pattern is.
Okay, so, let's go through the logic of this. You have two beams of light interacting in a material. This is the field distribution. This is the intensity distribution. Here is a picture of the intensity distribution. This is the intensity distribution. Now I say, let's assume that the material is nonlinear in the sense that there's an N2 response. That means that there will be a refractive index distribution that looks exactly like the intensity distribution. And I will call that a moving grating. You don't have to call it a moving grating if the words are getting in the way, but there is a refractive index distribution in the material that is moving either this way or this way. And then when light reflects or diffracts, your choice of words, but it's almost like a reflection. These are planes of high intensity. When this light reflects off of this grating, it will be diffracted into this direction. When this comes in, it will be diffracted into that direction. Quite remarkable, until you think about it. Quite remarkable that when these two waves interfere, they set up a grating that automatically couples this one to this one and couples this one to that one. Does that help? And if not, we talk later. Because saying it a third time is not likely to help. Right? However, detailed calculation, which I'll show you in a couple of minutes, shows that the same power is transferred from omega 1 to omega 2 as from omega 2 to omega 1, so that there is no energy transfer. Okay, so some of the power of this beam scatters into that beam. Some of the power from that beam scatters into this beam. But it's exactly the same amount of power in both cases. So there's no net transfer of power between the two beams. We'll do the calculation in a minute. So let's consider a slightly more complicated nonlinear response. And we'll consider a Debye relaxation mechanism. Or, that is the more dignified way of explaining this. It's also called a sluggish material. And what do we mean by sluggish? We mean that, well, if n is equal to n naught plus n nonlinear, then n nonlinear satisfies the following equation: tau dn nonlinear dt plus n nonlinear is equal to n2 times I of t. Okay, so this tau then is the response time. So you just look at this and you can sort of see what is going on. If the response time is very, very fast, if the response time is very fast, tau is very small, this term just disappears, and you're back to your old friend, n nonlinear is n2i. But if tau is very long, it takes time for the material response to develop. Now, what is a typical value of tau? Answer, there is no typical value of tau. For electronic response, tau is of the order of 10 to the minus 15 seconds. For the orientational nonlinearity, tau is of the order of a picosecond, and for Brillouin, or electrostriction, tau is of the order of a nanosecond, 10 to the minus 9 seconds. So depending on what, and it's a measure of sluggishness, right? And you can, and there are saturable materials in which saturated response for certain molecules tau can be as large as 10 to the minus 3 seconds. Okay, so this response time is all over the map, and it simply depends on what type of nonlinear material you use to do this to do the experiment. Now, what I want to do is to take this expression for the intensity and introduce it into this equation and solve this equation. So I want to solve for n nonlinear as a function of position and time. And if there, no, before I erase, because I need more space, but let me open this for questions. Yes?
Which I want to ask is about the interference pattern.
Yes.
I know that interference, you mean that it's a real interference? Because having interference needs to be coherent light.
Oh, yeah.
Having coherence means two frequencies be equal, also with same polarization. But here you have two omega 1 and omega 2.
Oh.
That interference or no, something just different?
Okay. Let's say it's coherent.
Okay.
Of course, take two lasers. If they're narrowband lasers, the bandwidth could be a kilohertz. It could be as narrow as a kilohertz. That means that over a millisecond period, the phase does not drift. So you have two different lasers. They're each well stabilized. They will form an interference pattern if you measure it on a time smaller than a millisecond.
Even if their frequencies are different?
Yeah. Well, now, we can debate whether you call that coherent or not. I mean, my theory friends say, no, that's not coherent, because coherent means that for an infinite length of time, they will remain in phase with one another. But I tell them, life is short. I've never in my life done an experiment that lasted an infinite amount of time. So it's whether the phase drifts over the time scale relevant to the experiment. I won't mention the name of my stupid colleague who argues this point with me. Okay, any other questions? Boy, do I know who I mean. And he's not from Ottawa. I better stop there. By the way, that was a really good question. I said that was a really good question that you asked. Because you had me worried. No, you didn't. You had me worried about how to formulate an answer. Okay, so I said we're going to solve that equation. So what we find is that n nonlinear is equal to this constant k times a1 squared plus a2 squared plus a1 a2 star e to the I q dot r minus delta t over 1 minus I delta tau plus complex conjugate, like so. Okay, you can check. Oh, it was easier to check before I erased it, but that is the solution to that equation. So so the denominator has a real and an imaginary part. That means that there's a phase shift between n nonlinear of R and I of R. So you still have this grating moving through the material, but there will be a phase shift between the intensity pattern and the phase pattern. So if this is the intensity pattern here, perhaps the phase pattern is shifted a little bit in position. So this is I of t, and the dotted line is n nonlinear of t. You can almost feel where this is heading now, right? You know that the energy flow between one field and another field depends on the relative phase between them. And if we can change this phase, maybe there will now be energy flow between the two. So we don't really need coupled amplitude equations for this problem. It just drops out if we just use the wave equation. So let's start with Laplacian of E minus n squared over c squared partial squared E with respect to t squared is equal to 0. And now for n squared, let's take n naught plus n nonlinear squared, and let's approximate this as n naught squared plus 2 n naught n nonlinear. So I've dropped the n nonlinear squared on the assumption that this is much smaller than this. Okay, so Okay, so there are two terms here. Don't forget, E has both an A1 e to the ik1 dot r minus omega 1t plus A2 e to the ik2 dot r minus omega 2t. So when you multiply E times this, the n nonlinear also has a spatial dependence. So when you multiply this by this, you get 4 terms. And some of these terms are of interest to us. So let's look at the part of I'll call this the starred equation. Look at the part of star that varies as e to the I k2 dot r minus omega 2t. So assume that you've written this out in its ugly glory and just look at the part that varies like this. And now let's make our slowly varying amplitude approximation. And what we get is dA2 dz equals I times this constant k times A1 squared plus A2 squared plus I n2k A1 squared A2 over 1 plus I delta. And now let's interpret these. So this first term here, there's an I here. So this first term gives an overall phase shift to the beam. So there's no energy transfer here. That's because the contribution is purely imaginary. Now you come down here and you see that this has both real and imaginary parts. And the real part corresponds to energy transfer. Because if it's real, then A2 will either get bigger or smaller as it propagates. So we have to take the imaginary part of 1 over I delta and multiply it by the I. And I will spare you the elementary algebra. Here's what you find in the end, using tricks that we've used all semester long, is that if I1 is k a1 squared and I2 is equal to k times a2 squared, we find that di2 dz is equal to k times a2 star da2 dz plus complex conjugate, which we can write as k times n2, well, it's a different k, called k prime, times n2 times delta tau over 1 plus delta squared tau squared I1 times I2, and this combination here, let's call it little g. Little g is a gain factor. And now if we plot g as a function of delta tau, and let me remind you that this is omega 1 minus omega 2 times tau. So we just want to plot this as a function of delta. So we get a curve that looks like this. This is the 100th time this semester that we've plotted this functional form, and it always looks the same. It looks like this, just like the refractive index dispersion. Let's call this peak value G max, and then G max is equal to N2 omega over C. And then, of course, by the same line of reasoning, di1 dz is equal to minus G I1, I2, well, let's write it all. di2 dz is equal to plus G I1, I2. Okay, so let's try to make sense of this. Let's assume that N2 is positive. If N, because this, okay, these curves will flip top to bottom depending on the sign of N2. Let's assume that N2 is positive. That says that you get gain, well, we define this to be the gain of I2. We get gain of I2 if I1 is bigger than I2. Then I2 is amplified for omega 2 less than omega 1. You'd say all is good, because that means that the low frequency wave gets amplified at the expense of the high frequency wave, and that is what you would have thought. except what if we now assume that N2 is negative? And of course, there are plenty of situations where N2 is negative. And then I2 is amplified for omega 1 less than omega 2. And that raises the obvious question, where does the energy come from? I'll let you ponder that for a minute. So it seems mysterious. If anybody thinks it's not mysterious, raise your hand, because it means either you're one step behind me or you're one step ahead of me. One might think that, boy, if this works, I'm going to go into competition with Ontario Hydro, and I'm going to create energy out of nothing. So what is the answer to this? Well, first of all, the Debye relaxation model is not a Hamiltonian model. So the Debye relaxation model does not require energy conservation because, well, if you want to think like a theorist, it's a time-dependent Hamiltonian that leads to this. So on the one hand, our theory should not have anything to say. In fact, although this one seems more striking, in a sense you should be equally concerned about this. What happened to the extra energy? Well, the resolution is that the implicit assumption is that you have a material system interacting with a heat bath, just like in thermodynamics. So the extra energy can be absorbed by the thermal motion of the material. Likewise, you can pull a little bit of energy out of the thermal heat bath. You can amplify the low frequency wave, thereby taking energy out of the material. Your first thought is, well, that could never happen. And then you say, wait, there's something called laser cooling. There are Nobel Prizes for people who did laser cooling. And this is one mechanism of laser cooling. In atomic species, you tune the lasers. I mean, they are not using the language of nonlinear optics when they do this, but they tune the laser to the frequency where the low frequency wave gets amplified at the expense of the high frequency wave, and the atoms get colder. Okay, isn't this cute? Isn't this nice? So I meant this as a pedagogical exercise, but the fact that this describes laser cooling, and I mean, in a very simplistic way, it describes laser cooling, I think is something that's very nice. Okay, any questions? Yes?
When I was looking at the equation, I had the feeling that anything I2 gained was because I1 was losing.
I'm sorry, say it.
The two equation at the top.
Yes.
Yeah, when I look at that, I see, okay, I2 in something, it's at the expense of I1. Am I wrong?
I didn't understand the question. When you look at this equation,
I get the feeling that I2, whatever I2 wins,
is, yes?
it is at the expense of I1.
That I2, wait, let's see. So I2 grows at the expense of I1 if G is positive.
Yeah.
Is that what I said? Or is that the opposite of what I said? No, I think I agree with you.
I think for me, the beam number 1 has some energy, the beam number 2 has some energy.
Yes.
And if the beam 2 gains, then it means the number 1 loses.
Right. So one of them gains energy, the other one loses energy. That's why there's a plus sign here and a minus sign here.
So now I don't see where the bath.
Oh!
Is.
This model did not explicitly include the bath. Because I postulated the Debye relaxation equation. I think Debye did as well. We just postulate this. If you wanted to derive a Debye relaxation equation, you would have to put in the interaction with the bath. And I've never done that in my life. If you had said this even 1 week ago, this would have turned into a homework problem. But I will write this down. Yeah, that's a really nice one. And the students next year, I won't tell them. Can we derive the Debye relaxation from, let me see, density matrix theory. One would assume we cannot derive it from Schrödinger's equation because that is explicitly a Hamiltonian system. But one could, but the density matrix has everything in it. So almost certainly one can, but whether you can do it cleanly or whether you make a bunch of ad hoc assumptions along the way is interesting. Thank you. Any more discussion? Let's see. So let me move on to another topic then. Yeah. Let's talk about optical phase conjugation. This was much more exciting 15, 20 years ago. But again, this is so illustrative of how nonlinear optics works that I want to talk about it. That's point one. Point two is you wonder why it was so exciting 20 years ago and you no longer see physical review letters about phase conjugation. And the reason is that it's not a research topic anymore. People who build lasers sometimes make use of phase conjugation to make their lasers work better. Now you say, why is it that you don't know that? It's because the lasers that use it are lasers we cannot talk about. Okay, and since I can't talk, well, no government has ever told me their secrets, let's say, but there are journals like Aviation Week, where it's like WikiLeaks. They say, we think the government is doing this. Okay, so there are huge, huge lasers that can shoot airplanes out of the sky. This was Ronald Reagan's dream, if you recall. You recall? Yeah. Yeah. You guys were probably quite young when Ronald Reagan was president. Maybe not even born yet? Okay, so Ronald Reagan wanted to have laser weapons to protect the U.S. against ICBMs, intercontinental ballistic missiles. And, well, my best understanding is that this is not the first line of defense for the U.S. But there's still big, big programs in high-powered lasers. And some of these lasers make use of phase conjugation. So let's just talk about how phase conjugation works. Still amazed about how anybody could make a whiteboard that works this poorly. Unless it's the eraser. Maybe next time I'll bring my own eraser to class. I mean, because these are the markers that we use all over campus. And I've never had this much trouble anywhere else. And let's start out just intuitively trying to figure out what we mean by optical phase conjugation. Let's start off with an ordinary mirror. For example, a metal mirror. And let's see what happens when a wavefront falls onto this mirror. Now, I don't want to show a plane wave because that would not illustrate the point I want to make. So let's say that the wavefront is a little bit distorted, and the wavefront, instead of being a plane wave, has this bubble in it. So this falls onto the mirror, and now when you ask, what does the reflected wave look like? It will look like this, because this part hit the mirror first, and then we'll leave the mirror first, and we'll look like this. Now, let's contrast that with a phase conjugate mirror. This would have the property that if this same wavefront holds on to a phase conjugate mirror, actually I drew it this way on purpose. A normal mirror can just be a surface, whereas a phase conjugate mirror is always a volume effect. A phase conjugate mirror would have the property that the reflected wave looks the same as the input. So an ordinary mirror flips the wavefront front to back. A phase conjugate mirror does not flip the wavefront front to back. So why is it called phase conjugation? Well, let's let this be the signal wave, and let's let this one be called the conjugate wave. So let's represent the signal wave as some amplitude, complex with polarization, e to the minus I omega t plus complex conjugate. And let's define the conjugate wave as EC, e to the minus I omega t plus conjugate plus complex conjugate. Let me introduce the abbreviation PCM for phase conjugate mirror. So for a PCM, we have the property that the conjugate amplitude is some reflection coefficient times the signal amplitude complex conjugate. So go home, think this one through on your own, and you can convince yourself that the process of taking the complex conjugate of a wavefront is exactly the distinction between relating this to this. They are related to one another by taking the complex conjugate of this field amplitude here. Now, we can write this in a different way. We can note that the conjugate wave at R and T is this coefficient R times the electric field amplitude of the signal wave evaluated at time minus t. I mean, just look at it by inspection. This is true. So we could call this a time-reversed wavefront don't take the name too seriously. That's my only advice. This has nothing to do with breaking time reversal symmetry. It's just a mathematical statement, and it's one that occasionally can be very, very useful to understand the properties of phase conjugation. It is what the incident wave now, is what the conjugate wave now looks like, what the signal wave looked like at time minus t. Okay, so why do people care about this? It's because, it can lead to aberration correction. I've always found it ironic that aberration is spelled differently from Abbe, the German scientist who worked on resolution. So Abbe did not work on aberration. Abbe did work on aberrations, but they spell their name differently. It's too bad. Okay, so why does this lead to aberration correction? Let's say you have a perfect wavefront, and it passes through some distorting medium. So the wavefront, after going through the medium, is distorted in some way that I will indicate like so. So just some strange modification of the waveform. Yes?
Normally, so a little r is the reflection coefficient.
Yeah.
So isn't normally the reflection coefficient a complex number?
Yes.
So in this case, is it purely real?
Oh, thank you. Thank you. I love these good questions. Words escape me. So if this turns into, no. If this turns into this, we're talking about the wave front structure. But if this turns into, that's an overall phase shift to the wave. So this would be for a complex R. So it changes the overall phase of the field, but that's not the degree of freedom we're interested in right now. It's the wavefront structure. Okay, so if this distorted wave falls onto a phase conjugate mirror, the reflected wave is going to look exactly the same, except going in the opposite direction. So when you pass through this distorting material, you will end up with a plane wavefront that looks like this. Let me see where I want my thoughts to be heading. I guess if you want, okay. I mean, that's just ball and spring picture of how things are working. You look at this, you say, yeah, I understand. If you wanted to do it mathematically, you could note that the wave equation is invariant t goes to minus t, because the wave equation says that the Laplacian of E is minus epsilon over c squared partial squared E with respect to t squared is equal to 0. So if you replace the wavefront by a different wavefront, but then that wavefront is going to propagate in this direction the same way that this wavefront propagated in that direction. Or this is the reversibility of electromagnetic waves, and it's because the wave equation is invariant under t going to minus t. So why would this be of use in laser development? Let's draw a generic laser. Let me draw it this way here. Here's the laser gain medium. No laser is 100% efficient. So you put a lot of energy into the gain medium, and at best, half of it comes out in terms of laser light, and the rest of it ends up heating up the material. So when you and the heating is non-uniform. If you look at the laser rod like this, well, the energy flows out. Maybe there's even a cooling jacket out here. So this is very hot. This is less hot. This point here would be still less hot. Well, you say, well, to first order, it's just like a lens. So I'll just take the cavity and refocus the cavity to get away with the lensing part of this. But needless to say, it's not a perfect lens. It's a highly distorting lens. So, and because of this, lasers are often limited in the repetition rate by thermal heating. The repetition rate can be limited to 1 kilohertz for some lasers that we have in our laboratory here, or a big ruby laser to maybe 1 hertz, or the Livermore laser to maybe once per day. And it's largely a matter of removing excess heat from the gain modules. So how could phase conjugation help? Well, instead of building the laser like this, let's say you build the laser by putting your curved mirror here, by putting your gain medium here, and by putting a phase conjugate mirror here. So let's see what would happen then. Two colors. Okay, so let's draw the wavefront. I messed up my drawing. let's remind ourselves what the field looks like inside of a laser resonator. The field amplitude takes the form of the end mirror. By the time it gets here, it has to look like this. So it starts okay, so here it's a plane wave, and it becomes more and more curved as it propagates until at this point here it matches the figure of the end mirror. Now, what if you have a distorting medium? Okay, so then you have the input that looks like this, and the output looks like garbage, but you send the garbage into the phase conjugate mirror, you get the same garbage inverted coming out, and you have a perfect diverging wave, in this case, leaving the laser cavity. Okay, so that's the idea of how you do it. And now there's dozens of ways of building the phase conjugate mirror that sits at this point here. It's often stimulated Brillouin scattering phase conjugation. And that's still a different story as to why stimulated Brillouin scattering would lead to phase conjugation. And that's a chapter in the book that we're not presenting in lecture this year, unless I run out of material. But that's half a joke. Okay, so that's okay. So that's the big picture view of what phase conjugation is and why it is potentially important. Now let's delve into the details and see how we might make phase conjugation work. Except maybe this is a great time for like a 5-minute break.